Let's continue to explore the definite integral. So when we first introduced the derivative, it was just a sort of a construct that was defined at a single point, but we quickly saw that the derivative actually gives you a new function because you consider the derivative at any point. Similarly, the definite integral also gives us a new function based on the function that we're integrating. And this is called the cumulative area function, or the area up to function more informally. And it's actually not a single function, but a whole family of functions, infinitely many functions. So if we start with a function f of x, we can make g of x the integral from a to x of f of t dt. Here a is a fixed point, x is our variable, t is a variable of integration. I can't use x as both the variable I'm integrating over and a limit of integration, and since I'm considering g to be a function of x, I can't integrate over x. I just introduce a new variable t for integrating over. And so for any value of a, we get a function g of x, which is the area underneath f of x between a and x above the horizontal axis below the function. So let's consider an example of this. Let's let this sort of piecewise linear function be f of x, and down here I've sketched g of x, the integral from 0 to x of f of t dt, so it's the area between 0 and x. And let's investigate how I sort of sketch this graph. So between 0 and this point, the function is positive. So as x moves to the right, the area is definitely increasing. So the cumulative area function should be increasing between 0 and this point. Between 0 and this first sort of dotted blue line, since the function is actually increasing, each incremental bit of x will produce more and more area as x moves to the right. So that's why the slope here is increasing. As I move to the right, the little bits of area that I'm adding are getting bigger and bigger. Until I get to this first blue line, here the function f of x is constant. So what happens is, as x moves to the right, each incremental bit of x adds the same little bit of area to my cumulative area function. So the graph looks like it has a constant slope. To the right of the second blue line, the f of x starts decreasing, so the incremental bits of area that I add as x goes to the right are getting less and less, but still they're positive areas, so the cumulative area function increases. Then finally, when f dips below the x-axis up here, I start actually subtracting these areas, so g of x starts decreasing because now I'm subtracting some area. Something to notice, when f of x is positive, g of x is increasing. When f of x is negative, g of x is decreasing. And particularly here, where f of x is 0, g of x has a horizontal tangent. Let's look at a real concrete example. Let's find the cumulative area function for the function f of x is equal to 2x, starting at a equal to 0. So the integral we're looking at is g of x is equal to the integral from 0 to x of 2t dt. And here is an illustration of what is going on. At least this is what's happening when x is greater than 0. Here is the graph of the function y equal to 2t. In the ty plane, we're going from 0 to x, so the area underneath this curve above the x-axis from 0 to x is this. This point up here is x comma 2x. That's relevant to us because this is really just a right triangle of width base x, and height is the y-coordinate, which is 2x. So this integral is equal to the area of this triangle, which is 1/2 times the base times the height, 1/2 x times 2x, and we simplify that to be x squared. So first of all, I would like you to verify that this actually holds for x less than 0. That's kind of an exercise in using some of the properties of integration that we've developed so far, and please continue to interpret it as an area. And if you've seen some integration before, please don't use that in showing that this is true. But I would like to notice one other thing, which is this. F of x is 2x, g of x is equal to x squared. So g prime of x is 2x is equal to f of x. That's sort of an interesting thing happening right here. The derivative of the cumulative area function is the original function. Okay, we've seen two examples of this cumulative area function. And in the first case, I was sort of suggesting to you that the original function was sort of acting like the derivative of the cumulative area function, in the sense that when the original function was positive, the cumulative function was increasing. When the original function was negative, the cumulative function was decreasing. When the original function was 0, the cumulative function had a horizontal tangent. In the second example, I came up with we did an explicit example of a cumulative area function, and we saw explicitly that the derivative of the cumulative area function was equal to the original function. Now, generally, it's not a good idea to take 2 points of data and make a generalization from that, but whatever, that's what we're going to do right now. Those two things suggest what is called the fundamental theorem of calculus. At least this is the first part of it. It says the following: if f of x is continuous, really continuous on an interval, but whatever, let's just say it's continuous. And if g of x is the integral from a to x of f of t dt, then the derivative of g is equal to f. The derivative of the cumulative area function is f. All right. Generally, I'm going to stay away from proving things in this class, but every now and again, there's something which is either easy enough or fundamental enough for me to sketch the idea of the proof. And this is, well, it's fundamental. It says so in the name. So we should at least think about why this might be true. Here's the deal. The formal definition of derivative says that the derivative of g is the limit as h approaches 0 of g of x plus h minus g of x divided by h. Okay, here is a graph of f of t, and let me interpret this g of x plus h minus g of x. G of x plus h is the area all the way up to x plus h from a. G of x is the area from a to x. So if I subtract the area from a to x from the area from a to x plus h, I'm left with just the area underneath this curve above the x-axis from x to x plus h. So that's what the numerator here is. It's this area. Now, since f of x is continuous, it turns out that as h gets closer and closer to 0, the area of this rectangle, this piece under the curve, is essentially f of x times h. It's a little bit bigger or smaller, probably, but it's so close that we can estimate it there well enough. So I can estimate this numerator here by f of x times h. H is the width of this rectangular-ish area. F of x is my estimate of the height. Then I'm dividing by h still, and that's equal to f of x. So as h goes to 0, it turns out that this approximation gets better and better, and so that this limit is actually equal to f of x. So the derivative of g is f of x. Great.